Hi, NA Physics, it's Mr. Neff. Let's talk about converging lenses this time. But before we do, where should you go whenever you're super cold? I'll tell you at the end of the video. Now, if you watched my last two videos about lenses, you saw the big difference between a converging and diverging lens is what it does to parallel rays. The converging lens, which is what this video is about, is going to take those parallel rays and it's going to converge them to a point that's on the far side, the observer side of the lens, versus the diverging one is going to take those same parallel rays and it's going to diverge them, make them seem like they came from a focal point that's on the non-observer side of the lens. Now, with all that in mind, let me show you how you would draw a ray diagram for this converging lens. A converging lens, just like the converging mirror, if you can remember, it doesn't do the same thing in every situation. So here's a case where the object is outside of the focal point. Like I said last time, what you want to do is you want to draw the parallel ray, but you want to draw it first. And so here comes this parallel ray, and it's parallel to the principal axis, just like we're used to. And then now, what does it do whenever it hits the lens? It is converged. It goes to the focal point. So not away from the focal point in the principal axis, but to the focal point. And so there's our parallel ray. Now, when you draw the chief ray, you draw straight through that vertex, straight through that center point, and you keep on going. And then when you draw the focal ray is going to go through the focal point on this side, hit the lens, and then refract out. And you're going to see that all three of those are going to converge to a spot. And what you've now done is you've located the image, and you've also drawn probably the most famous ray diagram known to human beings, and I'll show you why that is in a second. Look at what we have here now. Now, this time we have a real image. It's real because it's real light rays crossing, no imagination necessary. You have an image that has a DO that is, or DI that is positive. Here was my DO, and it was positive, and now because the observer, there's the observer observing this, and that image is on their side, so this is a positive DI this time. It's going to be a negative HI. And negative HI says that it's pointing down, pointing the other way from the way the original object was pointing, and it's inverted. You can also see that in this particular case, we have a magnification that's more than one because that image, I don't know how big it is, but it's bigger than that object is. So we have our real image. Because I say, this is the most famous one. A lot of times in movies, you'll see like a chalkboard full of physics. And if you know your physics, a lot of the times the physics doesn't necessarily go together. But one thing that you always see on those chalkboards is that ray diagram that we just drew. Sometimes it's on there with things that don't have anything to do with it. But it's there it is. And it's now that you know what to look for, you'll see it again. Now that's what you get whenever you're outside of the focal point. You get that real image. But what about whenever you're closer than the focal point? Well, when you're closer to than the focal point, same thing you got with a mirror. You get a virtual image that's magnified. Look at why. Here we have two of the three rays drawn. Sometimes it's a pain to draw all the rays. I'll show you how you draw the last one too, though. Here we've got a parallel ray. It's going out parallel, and then it's going to through the focal point, like we had last time. We also have a chief that's doing exactly what the chief did last time. And then they didn't draw this, but you could draw your focal ray. Remember, you're using each focal point one time. You could draw that focal ray like this along that line. It goes out, and then it goes parallel like that. Now, you're standing over here as the observer, and you're going to see that those are never going to cross. And so here again, you're going to use your imagination. You're going to take those back into the lens, and you're going to see an image that is virtual. And so I can tell that it's virtual if I'm a math type, because I can say that I have a negative DI, negative because it's on the other side from the observer, in addition to that positive DO. I know that it's upright though, because I have a positive HI measured up that way, and that means that the flame is pointed the same way as the original flame was pointed. Here's a second example where the magnification is more than one. I don't want to give you the wrong impression. That's not always the case, and I'll show you that on the simulator. Here's that same simulator that I was using last time from our friends over at O Physics, and I'll put a link to the simulator in the notes of this video. But you can see that here's our object, and it's near a converging lens. I can take that object and I can move it around, and as you can see, as I move this thing around, I'm changing the magnification, I am changing the image height, object height, and so forth. So let me get out of our way here. And so I can move this thing around and I can change those. Now, once I get, the focus is at 4 on this left side. And so now I'm at 8 or just slightly more than 8. And you can see that my magnification is just about -1. Negative because it's inverted, but 1 meaning that it's the same size as the original object. Now, if I go this side, now my magnification just became more than 1. And so that 2F point, or that center of curvature, that's an important point because that's where the magnification goes from being smaller than 1 to greater than 1. Now, it stays greater than 1 the whole rest of the way in here, but the thing about it is you get really a gigundo image. As that object gets really close to the focal point, you're getting a really huge magnification. And then once you're at the focal point, now that's an important point. Sometimes you're going to look at that and somebody's going to say, well, see, those rays are parallel to each other. And so because this chief is going right through the center, this focal or this parallel is going out that way, and they're essentially parallel to each other. And so somebody might tell you that there's no image being formed, but actually I disagree with that. I say that there is an image that's formed at infinity, and if you had a screen that was really far away, you'd be able to form a pretty clear image on that screen. Now, as I go inside of that focal point, now you see something. Now, all of a sudden, watch this. See how the HI went from being something massive, see this massive HI, down to something that was, and it was negative, meaning that it was real. Over here now I have an HI. Now it's still pretty massive, but now it became virtual. And so I went from on this far side of the focal point, I had a real image all the way, real, until I got to the focal point, and now I come in here and I say that it is virtual, and it's humongous. It doesn't even fit on this screen, but even if I bring it down here, you can see it's way back over on this left side of the screen. As I bring this closer and closer now, here I get an image that's it's magnified, it is virtual, it is upright. So to try to summarize all that for us, I like to think of 3 zones where you could put the object. Either outside of the center of curvature, outside of the 2F point. You could put it between the 2F and the F point, so between the center of curvature and the focal point, or you could put it inside of the focal point. If you're in this outside of the 2F point, it's going to be real, it's going to be inverted, it's going to be reduced. As long as you're outside the focal point, it's going to be real and inverted. And so real and inverted goes for this range too, except now this is where it's magnified. Right there where the object distance is at the 2F, you have an object that's a magnification of -1. It's inverted, it's negative, but it's 1, meaning that it's the same size. And then at the focal point, to me, it's an even more drastic change, because if you notice, other than the magnification, that's where everything really changes. You go from real to virtual, you go from inverted to upright, and so to me, that focal point is an even more significant spot along this whole thing. Inside of there, you're virtual, you're upright, and you're magnified. Let's try that on an example right before we leave here. And so here I have an object that's located 8 centimeters from a converging lens that has a focal length of 10 centimeters. The height of the object is 0.56 centimeters. What's the height of the image? Now, on something like this, we know we're going to use the thin lens equation, and a lot of people just jump right to the thin lens equation. My suggestion is to quickly sketch a ray diagram for it, so that if you do make a sign mistake, if you do make putting this thing into that spot, you'll catch it easier with the ray diagram. It doesn't take long. So quick principal axis, quick lens, let's say there and there are the focal points. there, that's 10 centimeters away from the lens on each side. We're going to put the object 8 centimeters, so say we'll put the object like this. I was supposed to make it 0.56 centimeters tall, but that would be super, super small, so I'll just go with this. And so now I would have a parallel ray that did that thing. I would have a chief that did that thing. Technically, I would also have a focal ray that would do this thing, and those three would all intersect each other back in here, some spot. Now, it looks like it goes back in there pretty far, and actually I probably don't have it as far back as I could have it. So I'm expecting a positive HI, I'm expecting a negative DI, and I'm expecting a magnification that's more than 1. Let's see if we get all of those things, particularly the HI, because that's what they're asking for. If I wanted the height of the image, that's pretty easy. I know that the magnification is hi-ho over negative di-do. And so if I wanted the HI, all I'd have to do is take the negative di, divide by the do. The do, they told me, is 10 centimeters, positive 10 centimeters, and multiply by the ho. And the ho is a 0.56 centimeters. So this is going to be pretty easy. As soon as I figure out what to put in that numerator, bingo, I'm done. I know that the equation, thin lens equation, is 1 over f equals 1 over do plus 1 over di. So how about I say that 1 over di is 1 over f minus 1 over do. So we're looking at 1 over f, 1 over 10 minus 1 over 8. And I could certainly do that one in my head. I could get a common denominator of 40, it looks like there. You know, I guess I could do it with decimals too. This is a tenth, and this is 0.125, so it looks like this would be negative 0.025. That's the reciprocal, that's a 40th, so it looks like the di is going to be negative 40 centimeters. I knew it was back in there. It should have been even farther off the left side of your screen. Now I'm going to take that negative 40 and I'm going to put it in here. See, the negative that's there from the equation is going to cancel out the negative that I have. That's good because I was predicting that I'd have a positive HI. And I did this one before I started the video, and so I know this comes out to 2.8 centimeters. Now we could just check that over on the simulator. We could come and make our focal point that negative 10 like I had before, and we could make the object at negative 8, and now I'm going to make it small. Let's see if I can make it to 0.56 like they wanted it to be. That's pretty good, pretty close. We're going to go with that and make the 8 as close as I can. There we go. And so, yeah, it's off the screen like we thought, but here's my DI of that negative 40, and there's my HI that's real close to that 2.8 that I had before. If I could get this right on 0.56, I'll bet that would be it. And there's that magnification of 5. I didn't show that before, but that's that ratio of those heights because that's that ratio of those distances. So I hope that helps you a lot with the converging lenses. And for the punchline of our joke, where do we go whenever we're feeling cold? Go in a corner. It's 90 degrees.